Okay, we're going to get started and we're going to continue on lecturing in the chapter that we're on, which relates to the study assignment that's scheduled for today. We're going to get into some of the idea of the total ionic equations, net ionic equations, and all that kind of stuff here. And then we will lay it up here for today, I think, at that point. First off, before we continue on, any questions on balancing equations? So clearly, you need to be able to balance equations. What we're going to pick up with right now really is starting talking about types of reactions and ways to classify reactions. And when we talk about a chemical reaction, there's really three reasons why a chemical reaction takes place. You could pretty much boil down to one of these three things happening in most reactions that you see. The first reason why a reaction takes place is the formation of a solid, or what is sometimes referred to as a precipitate, PPT. The second reason why a reaction takes place is really the formation of water. So you make water, which obviously is our H2O. And really the third reason why a reaction takes place is a transfer of electrons. So when we look at reactions, like I said before, you pretty much can boil down any reaction that you see to this is basically one of the three things happening, and that is really the reason why that reaction takes place. Now, we're going to talk about different types of reactions and different ways to classify reactions, but for the most part, all reactions fall under basically two big umbrellas of reactions. And the first major sort of reaction that happens where a lot of reactions fall under are what are known as double displacement reactions. And double displacement reactions have the general formula of AB plus CD. How do you know it is a double displacement reaction? It's pretty much the only reaction where you start with two ionic compounds. So if you see two ionic compounds there on the left-hand side of the arrow, you probably got yourself a double displacement reaction happening. And as we'll talk about and see, pretty much in a double displacement reaction, the positive ions just switch partners, basically. So the positive ions will switch partners and will give you really two new ionic compounds on the other side. Okay. Now, the double displacement reaction is sort of, if you want to think about it, a broad category of classification of a reaction. There is, when we look at reactions, more specific ways to classify the same reaction. And as we will see as we go through the rest of this chapter here, you could classify the same reaction sometimes three different ways, depending on sort of what you're looking at. Now, the double displacement reaction actually is the one that takes care of the first two reasons why a reaction takes place. And that is when these guys switch partners, one time you may make a solid is formed in one of these products. And that again is known as a precipitate. And in that particular case, that would become a precipitation reaction, which is a more specific classification of a double displacement reaction. It's still a double displacement reaction, but people will call it a precipitation reaction because you made a solid. Now, the other thing that could happen in this sort of double exchange that occurs is instead of making a solid, when these guys switch partners, one of these guys actually becomes water, and water is formed. And that very commonly occurs, as we will see, in acid-base reactions. So acid-base reactions or acid-base neutralization reactions is a more specific classification of a double displacement reaction. So between those two reactions, a precipitation reaction and an acid-base neutralization reaction, which both of them are double displacement reactions. Takes care of two of the three reasons why a reaction takes place. Either you formed a solid or you formed water. Now, the other category of reactions, sort of the big umbrella that other reactions fall under, are what are known as redox reactions. And redox reactions basically stands for oxidation and reduction reactions. And oxidation, as we'll get into, means that somebody loses an electron, and reduction means that somebody gains an electron. And what's happening in these type of reactions, the redox reactions, is the third reason why a reaction takes place. If somebody's losing and gaining electrons, we have electrons being transferred in a redox reaction. So in a redox reaction, we have electrons being transferred. Now, under the big category of redox reactions, you have a lot of classifications that you might be familiar with. You have your synthesis reactions, or your combination reactions. You have your decomposition reactions. You have your single replacement reactions. And you have your combustion reactions. So each of these more specific ways to classify a reaction, all are still having electrons being transferred, and they all fall under the redox reactions. So you could really think of all types of classification of reactions as basically falling under these one or these two umbrellas. Either it's going to be a double displacement reaction, or you got a redox reaction happening where electrons are being transferred. Any questions on that there? We're obviously going to go into each of these more specifically as we go through the rest of this sort of chapter here. All right, so we're going to first really start with and talk about tonight here. We're going to start with our double displacement type of situation. And starting with double displacement means that we do have to kind of think about some other aspects of what is going on. And that brings us to this topic, which is an electrolyte. And electrolytes are substances that, when they go for a swim in the solution, will break apart into ions. So they will break apart into ions. And because they break apart into ions, they are able to conduct electricity. The presence of those ions floating around in the solution allows it to conduct electricity. And there's different types of electrolytes. So let's talk about the different types of electrolytes that we have. We have a strong electrolyte. And a strong electrolyte will 100% break apart in solution. So if you have something that's considered a strong electrolyte, in the actual solution, you will not have the whole unit still together. So if you had like a sodium chloride solution, it would break apart into sodium ions and chloride ions. And it is a strong electrolyte, which means 100% of what you have in that beaker are just the ions floating around. You have absolutely positively none of these units still together. It will just completely break apart. And because it completely breaks apart, it produces a lot of ions. And because it produces a lot of ions, it will conduct electricity really well. The common example of conducting electricity really well is you have a picture of a light bulb, has some electrodes on it, and if you stick those electrodes that's attached to the light bulb into a strong electrolyte solution, the light bulb will turn on and actually be very, very bright. So you have a really bright light bulb. In fact, I think on this page there might be a picture of it there. That would be it right there. So if you kind of hooked up a light bulb with some electrodes, you stuck it into a strong electrolyte solution, that light bulb is going to turn on. It's going to be very, very bright, again, because there is just a lot of ions floating around in that solution. The next type of electrolyte is, and by the way, strong electrolytes are typically ionic compounds, also strong acids and strong bases are strong electrolytes. So what is our list of strong acids, which is a good one to know? Strong acids, we have hydrochloric acid, nitric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, and last but not least, their perchloric acid. Yeah. This list of 6 strong acids is a good one to know for this reason. If it's not one of those 6, it's probably a weak acid. It's a pretty safe bet. So, if you learn those 6 and it's not one of them, good chance it's going to be more of a weak acid. What about strong bases? Strong bases typically have hydroxide in them. And from group 1 and 2 on the periodic table, things like sodium hydroxide, potassium hydroxide, calcium hydroxide, etc. If you go to group 1 and 2 on the periodic table, go like lithium, go sodium, go potassium, hang a right to calcium, come down to strontium, barium. If you hook any of those guys up with some hydroxide, you probably have a strong base, yeah? And those are going to be strong bases, which will 100% also break apart in solution. That's why it is a strong acid or base. So if you had something like hydrochloric acid in solution, it would 100% break apart into H plus and Cl minus. And what makes something a acid is the ability to produce free floating H plus in solution. So since it's going to completely break apart, you just dumped a bunch of H plus into that solution, and that's why it's a strong acid. And same thing with sodium hydroxide, for example, which is a strong base. It will 100% break apart into sodium ions and hydroxide ions. Again, 100%. You have this, none of these guys in solution. And if you looked at that beaker, you would have a lot of sodium, but more importantly, you would have a lot of hydroxide ions floating around. And the presence of a lot of hydroxide ions is what makes something a base. And again, because this thing's going to completely break apart, it will influx into that solution a lot of free OH minuses, which makes it a strong base. So strong acids, strong bases, or strong electrolytes, typically speaking, ionic compounds also, when they go for a swim, will break apart. And that's because that is where we find, frankly, ions, is in solution floating around. So when they go in, they break apart and they float around in the solution. They get surrounded by water, which helps them float around in the solution. And you got a bunch of ions basically floating around. Any questions on that there? All right, so let's talk then about a weak electrolyte. A weak electrolyte will actually mainly stay together, but will produce some ions. So because it's able to still produce a little bit of ions in solution, it could also conduct electricity, but nowhere near as good as a strong electrolyte. So again, if you go to the light bulb example and you stick it into a weak electrolyte, the light bulb will turn on, but it'll be very dull. So we're just going to show you that picture there. It would be this one. You can see the light bulb turns on, but kind of looks like it's dying. But it's still able to conduct electricity because in that solution, you still have some ions floating around. So if we take something like HF, for example, which is hydrofluoric acid, is that one of my 6 strong acids? It is not. So I know it's probably going to be a weak acid. So that is how you could determine those things. When hydrofluoric acid goes in for a swim, it will break apart into H plus and F minus. For the most part, in that solution, this is what you have. You will have just a few of these ions. Yes, sir. Talk about acids. Everything in that area next to fluorine is all kind of strong acids. They are, yeah. Why? It's a good question. It actually has to do with if you look in that row base or group, you got HF, right? You got HCl, you got HBr, and etc., HI, and all that, right? So what makes something an acid is the ability to release an H plus into solution and let it kind of float around. So when you look at these acids, what actually determines how easy they can release that H plus or not is something that we talked about when we were doing bonding. It's the bond energy. Our bond enthalpy, right? If you remember that, where we added up all the bonds we broke and all the ones we made, we had a whole list of bond energy. And when you look at the bond energy for HF versus basically everybody else below it in that group, HF has a very significantly high bond energy, which means it takes a lot of energy to break that bond. And because it takes so much energy to break that bond, that's going to prevent that hydrogen from just popping off as easy as it is for like HCl to release that H or HBr to release that H. As you actually go down group 7 there, which is these guys, bond energy decreases as you go down the group. And that's why actually, even though we always talk about hydrochloric acid as being like the strong acid, actually HI is a much stronger acid because it has a weaker bond energy, which means between HI and HCl, the HI hydrogen is going to come off a lot easier. So even though we always think of like HCl as the strong acid, which it is a strong acid, but in terms of acid strength, it actually increases as you go down that group because of the bond energy. And that's the reason why for that one. Yeah. Other questions? You'll learn more about that in 200B. That's all chapter on, or part of a chapter on that bond acid strength. Other questions? All right, so back to this guy here. Let me just erase some of that there. Go. So when we do put HF in solution, it will break apart a little bit, but it will mainly stay together, which means if you were to sort of look at the beaker there and see what's floating around, you would actually see a lot more HF units than you would, say, see ions floating around. And that is why we typically keep weak electrolytes together, because when they go for a swim, they pretty much stay together. But they still, again, are able to produce a little bit of ions that are floating around in that solution. And because they're still able to produce those little bit of ions, they can still conduct electricity. They're still considered an electrolyte. But again, nowhere near in comparison, for example, to our HCl, which is a strong acid. It is just going to be 100% ions floating around. So there's going to be a lot more ions floating around in that strong acid solution than it is in that weak acid solution. Any questions on that there? So the other way that you know it's a weak electrolyte as well is you see the arrows here. They actually head in both directions. This is what is referred to as a reversible reaction. And when you have a reversible reaction, you actually have two directions. You have the forward direction, which goes from reactants to products. And in these reversible reactions, what happens is at some point you'll make enough products that the products will decide we want to go back the other way. And they will actually head back in the other direction, which is referred to as the reverse direction. They will eventually reach what is known as equilibrium, which means the rate of the forward direction will equal the rate of the reverse direction, also known as 200B, chapter 15, 14, the entire semester, basically. So 200B, talk all about equilibrium and these type of reactions. But here, to our aspect here, it is going to be a weak electrolyte. That is what you can see. And that's different than in a strong electrolyte, one-way arrows. Everybody's just dumping out on the product side. There's nobody coming back together. They're just going to completely break apart. In a weak electrolyte, they're pretty much just going to hang together, and just a little bit of it's going to break apart. And again, we'll have kind of both directions. Now, the last type of electrolyte, which is technically a non-electrolyte, is something that will dissolve in water, but will not produce ions. So because this thing will not produce ions, it will not conduct electricity. And obviously, if we take a look at our picture there, that is going to be our light bulb that is not on. Yeah, so if you put it in a non-electrolyte, it's not going to conduct electricity. We're going to get no light bulb basically turning on in that case. An example of that is sugar, right? Sugar, if you have a solid, you put it in water, will dissolve, right? But sugar is carbon, hydrogen, and oxygen. That is nonmetals. That is covalent bonding. No ions are going to be formed, right? So even though it will dissolve, it will not create any ions. And it's that lack of ions which does not allow it basically to conduct electricity. Any question on those type of electrolytes there? By the way, speaking of water, is water a good conductor of electricity or a bad conductor of electricity? If you have pure water. It is actually a bad conductor of electricity if you have pure water, because pure water is covalently bonded, no real ions, right? Clearly, just a safety note here for anybody listening on the video or in person, obviously the water that comes out of your pipes is not pure water, and it has ions in it, and you will fry yourself, yes, if you decide to blow dry your hair in the shower, right? So you don't want to do any of those things. Again, do not blow dry your hair in the shower. And that is because when they actually purify water, right, and kind of clean up water for us, they actually put ions in it. So they add even more ions to it in the sort of purification process of it. And it definitely will conduct electricity because there's ions in it and stuff like that. But if you have really pure water, it actually is a pretty bad conductor of electricity. Just like, for example, we looked at sodium chloride in its aqueous form, but if I had solid sodium chloride, it also would be not a great conductor of electricity because the ions aren't free to roam around. They're stuck together basically in the solid form. Only when you dissolve that in water, it frees up the ions to start floating around, and that is what helps basically conduct electricity and stuff like that. Any questions on that there? So take home message, don't blow dry the hair in the shower, right? All right. So as we talked about here, any ionic guy is going to 100% break apart into ions and be able to conduct that electricity. Again, our weak electrolyte. Here's another acid. This is acetic acid, which is the main component of vinegar. Also weak acid, also not part of the kind of 6 strong acids. So I know it's a weak electrolyte. So when you have that acid again in that solution, it's going to mainly stay together and break apart a little bit, as we see here. Again, our reversible sort of reaction occurring. All right. So how do ions kind of free themselves and start floating around? They float around through a process that is sometimes referred to as hydration. And what happens and how something like, say, our solid sodium chloride ends up as aqueous sodium chloride is water is involved. And water, as we know, is again a polar molecule, with the oxygen being more negative, the hydrogen being more positive. So when we dissolve something in water like sodium chloride, the sodium ions get surrounded by water, negative side, which is the oxygen, basically will surround it. And the chloride ions, when they go for a swim, will also get surrounded by water, but actually the hydrogen part of water, which is its positive side. Opposites attract, right? So that opposite attraction will do that. This is how sodium chloride disappears. It doesn't really disappear, it just dissolves. It disappears because there is so many water molecules around those ions, we can no longer see it, right? It is still there because we know if we heat it up, we will evaporate off the water. And now those ions have nothing to keep them apart and they will stick back together and your solid will reappear. But when you go to dissolve it, there's so much water molecules everywhere, it's not visually available for us to see. And that's why sometimes people think when they make a solution, it's a chemical reaction, and it's not. It's actually a physical change. And because everybody's still there, there's nothing, nobody has changed basically when you do that. So the water serves to sort of keep the ions away. It also allows them to dissolve into solution. We usually help this process along when we go dissolve something, we stir it, right? It does two things, adds a lot of energy, gets everybody moving, also throws a bunch of water molecules all over that ionic solid and helps those guys kind of peel off the ions into these sort of groups. All right, so as I mentioned before, non-electrolyte like sugar. Here's a table. You have a similar one, I think, in your book. We talked about kind of our strong electrolytes, weak electrolytes. I would say probably 9 times out of 10, if it's a weak electrolyte, it's going to be either a weak acid or a weak base is probably the most common weak electrolytes that you'll come across. So that's why I said earlier, if you could sort of identify something as being like a strong acid or strong base, and it's not one of those things, then it's probably safe to assume it's going to fall more on either the weak acid or weak base side, and that's probably going to be a weak electrolyte, and you want to treat it that way. Obviously, non-electrolytes, there's some examples of some non-electrolytes. Again, these things will dissolve in water. Something like methanol or ethanol will dissolve in water because it has an OH group, allows it to hydrogen bond with water. But again, there will be no production of any ions in that case, even though they'll mix and stuff like that. So solubility is really important. Solubility is the maximum amount of solute that will dissolve in a given amount of solvent at a specific temperature. When we talk about things being aqueous, that's pretty much the definition of something being a solution. And a solution is a homogeneous mixture. That means that everything looks the same throughout. Everything mixes, no problem. There's actually two parts to a solution. There is the solute, which is the smaller part of a solution. And there is the solvent, which is the larger part of a solution. Those two things together is basically what makes up a solution. So as an example, what we talked about a second ago, I had my water. I'm going to dissolve it in some sodium chloride, or sodium chloride, dissolve it in water to make a sodium chloride solution. Water here is the larger part. That is my solvent. The sodium chloride in this case would be my solute. How do you know a solution? What is the solute? It's pretty simple. It is the name of the solution. So if you have a sodium chloride solution, sodium chloride is your solute. If you have a potassium chloride solution, potassium chloride is your solute. So usually the name of the solution is the solute. I will not say 100% of the time water will be your solvent, but a lot of time water is the solvent for things that are ionic and things that are polar. So water is a really good solvent for ionic things and polar things. It's a crappy solvent for anything that's nonpolar. So you wouldn't use water for anything that's a nonpolar sort of molecule or solution because they will not mix. And we'll talk why that is in a later chapter, but they basically will not get together. So water works really well for ionic things and polar things. Nonpolar things actually need a nonpolar solvent. A simple example that we did a while back there on whatever experiment that was, where we had the different layers, right? We had like a hexane layer and we had like our Cl2 up there. Cl2 is a nonpolar molecule, right? Hexane is also a nonpolar molecule. And that is why we found it in the top layer, because they mix together, because they're both nonpolar and they end up there on top. When we did that, we'll look for the color change happening. Any questions on that? Okay, so we talked about double displacement reactions as a big category, and again, a more specific way of classifying a double displacement reaction, as I mentioned earlier, is a precipitation reaction. And again, no matter how you classify it, double displacement, precipitation reaction, or as we will see, acid-base reaction, the reaction is always the same. Positive guys switch partners. And we will make, again, 2 new ionic compounds on the other side. And in this case of a precipitation reaction, we will end up with a solid being formed when those guys come together. So for example here, if we take a look at this equation, we're going to take a little lead 2 nitrate, and we're going to react it with some sodium iodide. And I know this is a double displacement reaction because I'm starting with 2 ionic compounds. That's a positive guy, negative guy, positive guy, negative guy. This is the only type of reaction that pretty much starts that way. And again, we're going to switch partners here. So let's just say, for example, we didn't have this side of the equation given to us, and we just had the front side here. What we want to do is what we talked about earlier, which is we want to get the right formulas down first, and then we want to do the balancing part, right? So we're just going to assume that there is no coefficient there, and we're just starting with these 2 guys. So as soon as I understand that this is a double displacement reaction, the thing that you want to really think about is what are the basic ions that make up these 2 ionic compounds. So lead 2 would tell me I have a lead with a +2 charge. Nitrate, as you know, is NO3 minus. Those are the basic 2 units that make up lead 2 nitrate, right? Same thing with the sodium iodide, which is an ionic compound. That is basically made up of a sodium ion and an iodide ion. Those are the 2 ions that basically make that up. At this point, you can correctly predict what goes on the other side by writing the correct formulas when you put these guys together. So just like we did with nomenclature, I have a +2 for the lead, a -1 for the I. So I need one more I, right, to balance it out. And that gives me my proper formula that I have up here. Now, when I look at the sodium, that is +1 and -1. That is how I get to NaNO3. I do not have like Na2NO3 which sometimes people, again, try to balance and write the equations together. Now that I have all of the proper formulas down for my equation, this is the point where I should then go and balance it. So I'll just write the rest of it up on top here. We had our PbNO3 and our NaI, right? Now that I have it, I'm going to put and balance it. I see a polyatomic ion on the left of nitrate, 2 of them. I see 1 nitrate on the right. I'm going to put a 2 here to balance my nitrates. That then means I have 2 sodiums, which means I need a 2 here. Also means I have 2 I's, which is now it's balanced. And now I have a balanced equation. So that is what I was talking about earlier. Sometimes people, if they have to predict what goes on the other side of the arrow, they try to balance it and write the formulas at the same time. And again, you will get the wrong formulas probably a lot of the times. Any questions on that there? Now that we have this equation here, this equation, as we probably know, is what is referred to as the molecular equation. So this is the molecular equation. And in the molecular equation, we just write everything like normal as formulas and put it all together and balance it. This is what is referred to more specifically as a precipitation reaction because we made a solid. So overall, this is a double displacement reaction happening. It can be more specifically classified as a precipitation reaction because we made a precipitate. Remember, making a solid or a precipitate is one of the 3 reasons why a reaction takes place. So this is why this reaction actually takes place. Now, we could write another equation that actually describes what's happening when we dump all these guys into the beaker basically together. So we could write an equation which is sometimes referred to as the total ionic equation, because when we take something that is an ionic compound in a solution and it's a strong electrolyte, it will not stay together. It will break apart. So this guy here will break apart because it's a strong electrolyte into lead with a +2 charge. There are 2 nitrates. This 2 will come to the front and tell me that I have 2 of these nitrate ions that are floating around in the solution. This guy right here is also a strong electrolyte, which means it will break apart into 2 sodium ions and also 2 iodide ions. Again, this 2 goes for everybody behind it. Now, when I get to the other side of the arrow, I have a solid. A solid will not break apart. Otherwise, it would not be a solid. The only way it could be a solid is the positive and negative ions stuck together and fell out of the solution part, basically, the liquid part. So we will keep the solid together. We typically keep anything that is a solid, anything that is a liquid, for the most part, anything that's a gas or a weak electrolyte stays together when we're writing this type of equation. So if you're writing your total ionic equation, you have a solid, a liquid, or a weak electrolyte, you should keep that thing together. Now, this guy right here is a strong electrolyte, so it will break apart. I'm running out of room, so I'm just going to go underneath it. That will give me 2 sodium ions and 2 nitrate ions. This equation is what is sometimes referred to as the total ionic equation. It describes basically what is happening in the beaker, test tube, whatever you got going on there. Sometimes people call it the complete ionic equation, or sometimes people just call it the ionic equation by itself. When you look at the total ionic equation, you should be able to find on the left-hand side of the arrow and the right-hand side of the arrow ions that look exactly the same. And in this case, that looks like nitrate here. And this is nitrate. They look exactly the same. What else looks exactly the same? Sodium, right? Looks exactly the same on both sides. These ions that you find on both sides of the arrow that look exactly the same, and by the way, if you do it correctly, should be the same number on both sides. There's 2's on each side of those guys. Are what are referred to as spectator ions. If you are a spectator, you are just watching, right? You're not doing much. And that is the idea here. Our spectator ions are pretty much having a good time. They're off and just going for a swim, basically. Yeah, they're just swimming around the solution. They're not doing much, but just floating around. So what we do with spectator ions is we typically cross them out on both sides. They basically cancel each other out. And what we are left with is the third type of equation, which in this case is lead with a +2 charge. And our 2 iodides will come together to make my lead 2 iodide, which is this yellow solid. This is what is referred to as the net ionic equation. The net ionic equation is pretty much what is happening in this reaction. Although you dump a bunch of stuff together, it is, in this case, the lead ion from the lead 2 nitrate is going to go float around and find the iodide ion from the sodium iodide, and they're going to come together and fall out of solution as this yellow solid you can see here in this picture. So those are 3 types of equations that we use to describe what is happening in a chemical reaction, very commonly used in double displacement reactions. Molecular equation, just a regular equation like normal, all the formulas like normal. Total ionic, we break apart anything that's really a strong electrolyte, anything that's solid, liquid, really gas, or a weak electrolyte we keep together. We find our spectator ions, we get rid of them, and whatever is left should tell you basically what's happening here. And again, we see basically what's happening, formation of a solid, which is why this reaction is taking place. Those 2 guys are coming together. Any questions on those there? So get through this here. There we go. How do we know if we put things together, will we get a solid or will we not get a solid? We could use solubility rules to help us determine whether or not we would expect when we put 2 ions together, for example, should we get a solid? So there's a few different solubility rules, but pretty much there is things that are soluble, which means they will mix. And those guys typically will get the aqueous symbol next to them, which means they're solutions. There are things based on solubility rules, which are insoluble. Those guys will not mix together and will come together and make a solid, and they actually get the S symbol. There is also, when you look at certain solubility rules, ones that are sometimes referred to as being slightly soluble. Slightly soluble is pretty much what it sounds like. A little bit of it will dissolve, and most of it will not. So most people consider slightly soluble, which is sometimes abbreviated SS, as being more on the insoluble side than soluble. So if you happen to come across something that says slightly soluble, then it's probably going to be considered most of the time insoluble in a solid. So these are the rules. Basically, anybody in group 1 and ammonium, they are going to be soluble, which means they will get the aqueous symbol. There are no exceptions, which means if you see a chemical formula that contains anybody from group 1, anybody that has ammonium in it, you know it's going to be soluble, it's going to be aqueous, it's going to be a solution. You don't even have to worry about it. Also, things that contain nitrate and acetate will also be soluble. There are no exceptions, which means, again, if you come across a formula that has nitrate in it, has acetate in it, it's going to be soluble. It gets the aqueous symbol next to it. It also means that for the most part, it's going to be probably a strong electrolyte and going to break apart. Now, if you have something that has chloride, bromide, or iodide in the formula, it will be soluble, which means it will get aqueous. But in this case, there are a few exceptions. Silver, that is mercury 1, by the way, that is lead 2. Those are exceptions, which means that if you have any of those three guys hooked up with either chloride, bromide, or iodide, they will do the opposite, which means they will not be soluble. They will actually become insoluble and make a solid product. Same thing with sulfate. Sulfate is going to be aqueous pretty much most of the time, except if you find your sulfate hooked up with one of these guys here. Silver, calcium, strontium, barium are lead. It will then become the opposite, which is insoluble and be a solid. A question on how to use those rules. Now, there's also some things in solubility rules that are typically insoluble. So hydroxide is typically insoluble, which means you typically get a solid with those, except if you have basically group 1, which is our other rule on the other page, right? Our ammonium, which is also our rule on the other page. That's why something like sodium hydroxide is soluble, because sodium is group 1. These guys here, if you have calcium, strontium, or barium, are slightly soluble. Again, slightly soluble would lead to it being more considered insoluble than soluble. Sulfides typically will be solids, unless you are hooked up once again with our group 1 or ammonium, our calcium, strontium, barium. And lastly, carbonates and phosphates will typically be insoluble, unless, again, you kind of are group 1 exception. So the nice thing about these guys is the exception is really the rule on the other one, which is group 1 is soluble in anything. So again, if you remember that, you'll be good for any of these sort of exceptions because you'll come across it. Any questions on that? So if I take something like iron 3 phosphate, and I react it with no, I don't want to do that. Try that again. Say if I take actually I'll do copper to nitrate, and I want to react it with ammonium phosphate. Write the products here, balance the equation, and predict the states of everybody here. Okay, so let's take a look. So first off, you should hopefully recognize this as an ionic compound. So that's a positive negative guy. That is also an ionic compound. So we have two ionic compounds, which should automatically scream to you, this is a double displacement reaction. So we're going to switch our positive partners here with our guys. So again, as we talked about, you want to make sure that you get everything written down correctly. So you just want to start with the basic ions for each of these. So our first guy, that is copper with a +2 charge, and that obviously is nitrate that we have for our first guy. For our second guy, that's ammonium, which is NH4 plus, and that is phosphate. Again, at this point, I'm just trying to get the right formula, so I don't really care too much about the balancing part of it at all. We're going to switch partners, so we just want to put them together correctly. So those two guys should come together, and that's going to be a +2 and a -3, which means the common number there is going to be 6. So maybe I'll just write it here. NO3 2 plus NH4 3 PO4. And now when I put this together, I will need 3 of the coppers and 2 of the phosphates. Gives me my proper formula there. Now we're going to put these guys together, and that again is only +1 and -1. That is not like parentheses NH4 3 and a parentheses NO2 2. That is just a plain old NH4 NO3. Yeah, so those are again the correct formulas. Now that I have the correct formulas, now I could go balance it, right? And if I'm going to balance it here, I do have some polyatomic ions. Maybe that'll be helpful. I'll try let's see here. We got NO3 there. There we go. That's a 3. We'll go with maybe try the nitrate here. Maybe we'll go with like a 2. And then obviously that's not going to work. So I can see my 2 and my 3 means probably I need this as to be the 6. So a 6 of those would mean I need 2 of those. And then what we got there, 3 of those there, I think. Yeah. So that should be a balance. That should be a 2, I think. Any questions on that? So we got 3 not carbons, coppers on the left. We got 6 nitrates on the left, 6 nitrates on the right, 6 ammoniums on the left and 6 on the right, and 2 phosphates on the left and right. So we are balanced. Any questions on that there? All right, so at this point, we can now use our solubility rules here to determine what's aqueous, what is solid, if there is a solid. We have copper to nitrate. So as soon as I see nitrate, that's one of those rules on the previous page. That is soluble in everything. There is no exceptions. So as soon as I see that nitrate, that's pretty much all I have to worry about. And that's going to get the aqueous symbol there. It's going to be a solution. Same thing here. I see ammonium, which also is on that previous slide as being soluble in everything. There's no exceptions. So that will tell me it's going to be aqueous as well. What about my copper 2 phosphate? That will be solid, right? Phosphate is going to be solid unless it's hooked up with group 1 or ammonium, which it is not in this case. So that is going to be my solid or my precipitate here in this reaction. And ammonium or nitrate, either one you want to look at, are going to be soluble in everything. So you don't really need to actually do both, but they both will be aqueous. Any questions on how to write the equation, balance it, use solubility rules to predict? Solubility rules will probably be provided for you in some form. You just need to make sure you know how to use them. Yes. Okay. So let's answer this one here. For each of these, are they going to be soluble or insoluble in water? Okay, so let's take a look. Now, when you use the solubility rules, you might not be able to find both things maybe on the rules, but you should at least be able to find one of the two things at least. So in this case, really just looking here, we can actually find both in this case. But really, when we hit the first one, which is potassium, that is group one. That is soluble in everything. There's no exception. So this guy should be soluble. It should get the aqueous symbol. Really, because of the potassium there, it's a no exception type of deal. Now, when we look at this one, we probably will find the bromide there on the list. And as you know, the bromide is soluble in everything except three exceptions, and silver being one of those exceptions, silver, lead, and mercury. So even though it normally is aqueous, because this is one of the exceptions, this guy would be insoluble. I have a solid, so this guy would not be aqueous because it is an exception. Any questions on that one there? Coming here, chloride is probably what we're going to find on the table. Chloride is soluble in everything except, again, those same exceptions, silver, lead 1, and mercury. Mercury 1 and lead 2. That's why it didn't sound right. That is not one of those exceptions in this case, which means this guy is going to be aqueous and soluble. Looking at the next one is lead 2 nitrate. That nitrate right there is soluble in everything. There's no exception, which means it will be aqueous and will be soluble. Yeah. Lastly, looking here, that is sulfate, and that is what we want to look at. And if we look at sulfate, it is right here, which is soluble in everything. But there is an exception, which is our lead, which is what it is in this case. So because it normally is soluble and it is an exception, it will be the opposite, which means it will be insoluble in this case. And it gets the solid notation. Any questions on that there? All right. So again, our rules for writing our net ionic equation: get the balanced molecular equation. You want to break it apart into your total ionic equation, and you then want to find your spectator ions, and then obviously end up with your net ionic equation. So why don't you do this one? Why don't you write all three of them? We're looking for the balanced molecular equation, the total ionic equation, and the net ionic equation, right? Also, all right. So we do want to start with the proper formula. So silver is +1 and nitrate is -1. So that should be our proper formula there for silver nitrate. Going to react with sodium chloride +1 and -1, which will put it together. Once again, if you're not sure what type of reaction this is, that's an ionic compound. That's an ionic compound. So again, that should tell you it's a double displacement reaction. We're going to again swap partners here. We want to make sure we have the proper formulas on the product side. So silver, which is +1, and chloride, which is -1. When that comes together, it gives us AgCl. And sodium, which is +1, and nitrate, which is -1. When that comes together, we get NaNO3. We just need one of each of those. Any questions on that part of it there? And again, as I mentioned before, you just want to look at the basic units of those ions. And in this case, we had silver, we had nitrate, we had sodium and chloride. And again, we just want to put them together just like we did with nomenclature at =0. We want to make sure it's balanced, which in this case, it actually is balanced. We also want to put our states in here. So I see nitrate, which I know is soluble in everything. So that's good. Sodium also going to be soluble in everything. So don't really need to look any further than that. What about my silver chloride? That's going to be it is going to be a solid. So again, chloride soluble in everything except silver, lead, and mercury. In this case, it is silver being the exception. So it goes from being soluble to being insoluble. Once again here, sodium and nitrate, they are both soluble in everything. which means they will get the aqueous symbol. Any questions on that there? That obviously is our molecular equation, right? Now for our total ionic equation, we're going to break apart anything that is a strong electrolyte, right? We can keep together anything that is solid, liquid, gas, or a weak electrolyte. So this will be silver with a +1 charge. This will be nitrate with a -1 charge, as that will break apart. So will our sodium chloride break apart into a sodium ion and a chloride ion. Once again, our solid will stay together, otherwise it would not be a solid. And our sodium nitrate will break apart into ions of a sodium and a nitrate. This would be, again, our total ionic equation. This is the equation where we can identify our spectator ions from. And in this case, we have nitrate on the left and nitrate on the right, which would be a spectator ion. We also have sodium on the left and sodium on the right, which would be a spectator ion. So both of those guys are going to be our spectator ions here. So we do scratch them out, and we are left with our net ionic equation here of the silver ion coming from the silver nitrate. We'll go find the chloride ion that's coming from the sodium chloride, and they will actually come together and form a solid silver chloride in this case. Any question on any of those equations? By the way, a very common mistake people make is in the total ionic equation, the net ionic equation. They don't write the charges for the ions, yes? So if they are ions, they need to have charges. Yes? Otherwise, they're not ions, right? So definitely in the total ionic equation, net ionic equation, anything that is an ion should have the appropriate charge. Any questions on that one there? All right. Let's try one more here to wrap it up with. Write the equation for the precipitation reaction between potassium carbonate and nickel 2 chloride. So let's do balance equation, total ionic equation, and net ionic equation. And what are the spectator ions for this? Again, we got to come up with the equation here. We're going to react potassium carbonate. So we just want to take kind of like our nomenclature approach. Potassium is group 1, +1. Carbonate is CO3, 2-. So again, when we put that together, we need 2 of those guys. So that's going to give us K2CO3 as our formula. Nickel 2 chloride. The nickel 2 means I have a nickel with a +2. Chloride is -1. So again, we actually need 2 of the Cls. So that's going to give us our proper formulas here to start with. At this point, once we have our proper formulas for our reactants, we should be able to identify this as a double displacement reaction because we have 2 ionic compounds. So we're going to switch partners. That means that really the potassium and the chloride are going to come together, and that's a +1 -1, which will give us KCl. Then the nickel with a +2 and the carbonate with a -2 will come together, which will give us NiCO3 in this case. Any questions on how I got those formulas there? All right, so now that I did get the formulas, now I'm ready to balance, right? So now I want to balance it. Looks like I just need like a 2 perhaps right there. That will give me 2 potassiums, 2 chlorides on each side, 1 carbonate on each side, and 1 nickel on each side. We can now use our solubility rules to determine what everything is here. So I see potassium in the first one. I know that's going to be aqueous and soluble no matter what the situation is. I see nickel 2 chloride. The chloride is going to be soluble in everything except for lead, mercury, and silver, which is not the case. By the way, I also knew it from the problem. It said aqueous, so I knew that they were aqueous to begin with. Potassium chloride, potassium soluble in everything, will be aqueous, and it is here our carbonate that's going to be insoluble, and that is what's going to make this a precipitation reaction, which is again a double displacement reaction. Any questions on that? Yeah. It does, as long as it's on the correct side of the arrow. It's okay. Doesn't matter the order that you put it, as long as it's on the correct side of the arrow. All right, so that would be my molecular equation. I can now do my total ionic equation by breaking up anything that is a strong electrolyte. So this guy would break apart into 2 potassium ions. That 2 would come to the front, plus 1 carbonate ion. The nickel 2 chloride will also break apart into nickel 2. And again, this 2 will come to the front and be 2 Cl minuses. Remember that these are ions. There is no Cl2 minus, yes, when you do this part. So again, that 2 needs to come to the front of it. Now, here on the other side, my potassium chloride definitely is a strong electrolyte. It's going to give me 2 potassium ions and 2 chloride ions as they break apart. And our solid, as we talked about, will need to stay together. Otherwise, it would not be a solid in this particular case. This would be my total ionic equation, right? My spectator ions in this case are, if I look on both sides, I see potassium and I see chloride here on both sides. Again, as I mentioned before, you should actually have the exact same amount of those ions on both sides. Otherwise, you screwed up balancing or something like that. So these would be obviously our spectator ions. They would cancel out on both sides like the arrows and equal sign. That will leave us the nickel 2 coming together with the carbonate here to form nickel 2 carbonate, which is a solid. This would be my net ionic equation here in this case. The answer to the question is it really doesn't matter necessarily which one you put first, but by sort of normal rules of operation, we usually go positive, negative. So usually we write the positive ion first and the negative ion second. It's not technically wrong if you did it the other way, but that's just why normally we kind of write it that way. Question on any of those 3 things there? All right.